This is Carolyn. Last time you saw her, she was hanging off of the ceiling right there. And this entire thing is a mostly printed design. The trick here is that I'm using this half scissor lift mechanism that saves me from having to use like super high torque motors and also reduces the load on these 3D printed parts. But one of the core pieces of this design is this link right here that goes from the carriage up to the next arm. Because I was quite tight on space, I had to design it with a curve going in two directions, going in, out, around other parts. So this right here is the original design that I used. And as you can tell, this is not particularly rigid. And as a result, even with these reprinted parts that are thicker, stronger, and now are printed from a carbon fiber reinforced PETG, there is still some bounce in the design, especially down here. And the closer we go to this being flat, yeah, the less rigid the entire setup is. But there are other filaments that are promising to be even more rigid. Stuff like PPA-CF or PPS-CF. There's also polycarbonates, there's other nylons, other PETGs that are carbon fiber reinforced. So even though I know that I need to redesign this part for whatever this project is going to turn into, I still want to know like what is the most rigid filament that I can print with, because making parts that are rigid is something that is going to come up over and over again. Back with the Filament series, I've already done some synthetic testing on filament rigidity. PETG scores rather low, but now I have a real use case that I have a real world example from. Don't want to reprint all of this stuff in, how many did I print? At least 20 different filaments, especially since printing a part this large or that large in something like the PPS-CF is going to be like a 30 or 40 euro part. So I've made a quarter scale, third scale roughly representation of this exact part, and we're going to see which of these filaments actually would be the best suited for this application. Now, while it is pretty amazing how much you can do yourself with 3D printing these days, there are still some parts that will need to perform a little bit better than what you can realistically do at home. So just get them made by today's sponsor, PCBWay. They make it super easy to order not just PCBs and 3D prints, but also CNC machine parts from aluminum, steel, titanium, or plastics. They also do flat or ready-to-use bent sheet metal parts made to your specs, machined carbon fiber plate, or even batch-produced injection molding. Being able to rely on PCBWay to use affordable, high-performance parts for your builds and projects is an absolute game-changer for what you can achieve. So check out how you can profit from using PCBWay at the link below. And to test all these parts, of course, we need some sort of a jig. And here it is. This is basically a miniature version of what's going on in the real arm. Yeah, honestly, I don't think I needed the bearings. These three different positions provide three different angles that I can mount the test sample in. But essentially all they're doing is providing different gearing ratios between the test weight and the load that that link is seeing. And then we apply a load from here, and it is bending in all sorts of good ways. And then to measure how much everything is bending, we've got the dial indicator that gets fastened to the side here, like so. And then we apply force and... ah, crap. This thing moves. Just printed a shorter one. Same idea. Perfect. So the question now is, how much weight should I be applying to these samples? I've had a quick rummage through my shop and I found this. This is brass, and it is just shy of bottoming out the PETG, so yeah, I think that's pretty good. So here's all my test samples printed. I did print all of these on the Bamboo H2S because I did want to include the PPS-CF and PPA-CF filaments. And the only printer I have that can print those is the H2S, which means to stay consistent, that is the printer I used for everything. These are all printed with the default 0.16mm profile. The only thing I changed is I increased the bottom solid layers to give it a consistent shell. Everything else is just the standard print profiles or the recommended temperatures if there was not one. So starting out with PLA, these are two different PLAs. One is Voxel PLA Pro and the other one is Bambu Lab PLA Tough Plus, just to see if there's a difference, whether this is a more elastic type of PLA, because typically PLA is on the rather rigid side. And to compare a carbon fiber version with that, I am using the Pure Poly carbon fiber PLA that was included with the Magneto. But there's another type of PLA, and that is HDPLA that Protopasta are known for making. This is a PLA that I think doesn't have any of the elastifiers in it that the sort of tough type PLAs are known for. And the special thing is that you can heat treat it. So I did that. I printed 2 parts, both from the standard PLA with nothing in it and the carbon fiber reinforced one. For that, I'm grabbing some quartz sand as opposed to just chucking them in the oven in the open air, so the sand has a chance to distribute the heat more evenly and also sort of restrain the part while it is being heat cured. I'm completely burying these parts in sand, then I'm preheating the entire thing to 80 degrees and finally giving them half an hour at 100 degrees. You will find heat treat recommendations ranging from 60 degrees for 12 hours to 130 degrees for 10 minutes. I'm choosing the middle ground here, and I'm hoping this will keep warping in check while also giving me most of the benefits of the improved rigidity and strength. One of the things that typically happens when you heat treat HDPLA is that it shrinks in the XY direction and slightly grows in the Z direction. But I think the sand method actually worked pretty well, and keeping the temperatures low also seemed to help. So these only shrunk by, I measured these, about 0.5% for the carbon fiber one and roughly 1% for the non-reinforced one. And you can tell how much more rigid it is just by the sound that they make. So let's drop the standard HDPLA carbon fiber and the treated one. So the heat treating in this case, I think, did a really good job. The way that I'm measuring these is that I'm first loading the part with the weight and then measuring how far it springs back. And that just makes sure that both ends of our sample are seated on the pins properly. This is how much the voxel PLA deflected in each orientation. I can compare that to the median of how all the other filaments performed, and then average it across the 3 orientations. In this case, the voxel PLA got a combined score of 111%, meaning that in this test setup, the sample should be able to take an 11% higher load than the median average of the rest of the samples for the same amount of deformation. Or simply put, the sample is 11% more rigid. The 111% for voxel PLA are a lot higher than the 77% that Bambu Lab's Tough Plus PLA gets, meaning the Bambu PLA is clearly modified to be tougher and less rigid. The PO Poly Lancer carbon fiber PLA easily beats both of them at 122%, but it ties with the HDPLA in its untreated form at 120%. Interestingly, with the way that I annealed it, it did not improve after it came out of the oven at just 116%, which is within margin of error. The carbon fiber HDPLA performed really well at 158% and improved even more after heat treating, jumping up to 176%, easily beating all the PLAs we've seen so far, both in its unannealed and in its annealed form. Next up, PETG, and there are a ton of PETG variants out there. PETG, however, is known as one of the least rigid filaments, and the interesting thing is going to be how much the carbon fiber reinforcement helps. Judging by sort of what sound they make, that's Prusament PETG-CF, compared to the HDPLA, yeah, it is not very promising, but I have plain PETG from dust filament, just clear standard type, and then 3 different types of carbon fiber reinforced PETG. One from Prusament, one from Apprinter Pro. They don't sell this anymore. And Colorfab XT-CF20, which is also a polyester-based material. The part printed from plain PETG sets a new low score at just 66% of the median bend resistance. Prusa's PETG-CF gets 82%, the Apprinter Pro PETG-CF is 111%, and the Colorfab XT-CF20 scores 96%. So even though these are carbon fiber reinforced filaments, they are still quite soft overall. For ASA, I just have standard ASA from Prusament. And just like the closely related ABS filament, ASA is also on the more impact resistant side, scoring 75% of the median. My polycarbonate samples are also printed from Prusament, both the unreinforced plain version and the carbon fiber reinforced one. Polycarbonate is known to be more of a tough, chewy type material, so it's going to be interesting to see how much the carbon fiber reinforcement does for rigidity. And as expected, plain polycarbonate only comes in at 77% of the median rigidity. However, carbon fiber reinforced polycarbonate scores a 101%, making it the meanest of all filaments. carbon fiber doesn't just make filaments more rigid, it also makes them easier to print because it prevents them from warping while they're on the printer. Plain polycarbonate is right on the edge where it gets tough to print without a heated chamber, and having a carbon fiber reinforced version might just make it more accessible to more printers that don't have that active heating. Both of the polypropylene PP prints were pretty tricky to get out. The unreinforced plain no-name PP was pretty much impossible to print, and the Prusament carbon fiber reinforced PP was also really tricky, and I just realized I actually need to retry this print. I didn't do that so far. So if you see some testing now, you'll know that this will have succeeded. Testing, 1, 2. I did get the part to print. It is not the cleanest part ever, but as far as rigidity goes, well, I've had some flexible filaments that put up more of a fight than the carbon fiber reinforced PP. As a result, it gets the lowest score yet at just 41% of the median rigidity. But even that result should be taken with a grain of salt, because it did bottom out the test jig on the very most extreme position, but also it's one of the few filaments where the weight I was applying was enough to keep it creeping until I took it off. And yeah, I couldn't get the plain polypropylene to print well. This basically feels like a stick of hot glue. So getting into the more difficult filaments now, these are the nylons. Well, actually this one is also nylon. This is the Sunlu Easy PA. I did dry all of these filaments for at least 4 hours, and the trickier ones like the nylons overnight at 65 degrees Celsius. Apparently that was not enough for the Sunlu Easy PA, so it is really stringy, though the Prusament PA11 carbon fiber also does have quite some stringing. Also, I do have the Bambu Lab PPA-CF, which is a high temperature nylon type, and that one did print a little more cleanly. Also, this does feel incredibly rigid compared to the standard PA already. There are quite a few different types of polyamides, so PA6, 6.6, 11 I think is what the Prusament is based on. So just saying this is nylon or polyamide doesn't really tell you a whole lot about the material itself. The Sunlu Easy PA not only is stringy, but it is also very soft at 55% of median. The Prusament PA11CF scores a much more respectable 86%, and the Bambu Lab PPA-CF scores a whopping 169%. Every time I stick my head in like that, I'm double checking that what I think I'm seeing is actually what the dial gauge is showing. And yeah, the PPA-CF isn't just the most expensive filament in this test, it's also the one that turned out to be the most rigid without any post-print treatment. Finally, Bambu Lab PPS-CF, let me drop this one. So good. This does sound like it's the most rigid one, but along with the Bambu Lab PPA-CF, it is also the most tricky to print, especially in the Bambu Lab machine, where it has that tight curve around the Teflon tube as it feeds into the extruder. These so far have always cracked when the printer homes itself, so either you have to keep pushing the filament in as the first layer starts, or what I ended up doing is unclipping that tube and just giving it a little more wiggle room for these filaments that keep the tube in place anyway, because they are so rigid as a filament as well. But even though PPS-CF makes that really nice clinking sound when you drop it, its bending performance is closer in line with a carbon fiber reinforced PLA. It scores 141% of median. So, what have we learned? Well, the original question was, what is the most rigid filament? And that answer is PPA-CF. Well, this is clearly the most rigid filament that you can get off of your printer, hands down. Unless you also count the HTPLA-CF once it has been heat treated, because this actually does produce parts that are slightly stiffer, slightly more rigid than the PPA-CF. And interestingly, it does it, with an extra post-processing step, but it does it at just over 1/3 as much per kilogram as the PPA-CF. So this gives you more rigid parts at a fraction of the cost. And that opens up a different way of looking at these results, because yes, some of these filaments are more rigid than others, but there is a much, much bigger gap in how much you pay for the filament itself. And once I rank them for rigidity per cost, then the entire thing flips around. With PLA, plain old, non-tough, just non-reinforced, just basic PLA, being more than twice as good as most of the other filaments in how rigid of a part you get versus how much you pay for it. In general, the more high-end a filament is, the less value for money you are getting. But I'm not saying that like high-end filaments like nylons or PPs are useless. It is just that they also have some other properties that you might want, like chemical resistance, and polycarbonate or the nylons or PPS also have really good temperature resistance, which is something you might need. Nylons do tend to absorb moisture from the environment, from ambient humidity, and that drastically changes how well they perform. Typically, it makes them a lot softer, which is not something I've compensated for here. These parts were printed and tested within 48 hours of being printed. So I can also look at how much rigidity the two HDPLAs gained. These are different generations of HDPLA between the plain and the carbon fiber ones, so they do behave a little differently. The plain HDPLA, within margin of error, actually gained no rigidity at all. And the carbon fiber HDPLA from heat treating gained about 10% rigidity with minimal shrinkage, warpage. So that is something that I think is definitely worth it. And again, it produces the most rigid parts out of all of these with that extra heat treating step. I've also looked at how the carbon fiber changes the stiffness of these parts, because I do have 5 different filaments that I have in a plain and a carbon fiber version. And on average, it improves the rigidity of these parts by about 40%, which is pretty good. The materials that are less rigid by themselves profit more versus something like a PLA, which already is quite stiff by itself, that profits less. However, if you look at cost versus rigidity, the extra cost for paying for carbon fiber in your filaments is not really worth it. I mean, I've previously shown that adding shredded wind turbines to your filament doesn't really improve strength because the fibers are pretty short. So the main structural component for strength is still the base polymer itself, but it does improve rigidity. The real kicker here is that we're 3D printing. We are not limited to this exact setup and this exact geometry even, because we can design these parts pretty freely. So I did 2 more things that I think put all of this in context. First of all, I just printed the same part with 100% infill versus the 15% that I used in all the other parts. I did that with the Prusament polycarbonate. And this used about 75% more filament and gave a 41% improvement of rigidity. So if that is all the space you have, then yes, adding more material does make your parts more rigid. But in almost every application that you will run into, material is always best used in the shell of the part, as far on the outside of your part as possible. And if you just add more infill, then that is a bit of a waste of material. So what you can also do, if you have the space, is just print a chunkier part. Make your part thicker, larger, more girthy, and especially in bend loads, which is what we have a mix of here. So we both have a bending load and a compressive load on this. Making the part 41% larger in both dimensions, both the width and the height, that used about 65% more material, so less than just going to 100% infill. But it almost tripled the rigidity of this part. So if you have the space to just optimize the geometry of your parts by making them thicker and girthier and larger and chunkier, then you can pretty much negotiate any sort of downside of rigidity that you might have from using a cheaper, a lower end material. Because that's the thing that I realized. The span of how rigid the worst and the best filament is not that large. So you might look at data sheets and be like, oh, this material is so much more rigid than this other one. And yes, that is true. But the difference really is just about a factor of 2x from PETG to the temperature-treated, heat-treated HDPLA-CF. So that is about 2x. This one bends half as much as this one. However, this chunky one bends 1/3 as much as this one. So just with a small geometry change, you can much improve your part's rigidity without opting for a higher end filament. So in a real world use case, I think the order of optimization should be, first of all, if you have the space, just make your part chunkier. Add a little more girth, make it a little thicker. That is, for example, what I did on Caroline. These arms are pretty thin here, so I made them thicker. I also changed the geometry. I added a reinforcement piece. So that was step number 1. Then the second step should be use a thicker shell. That's where that material matters the most. And if you've not exhausted that option yet, then yeah, make that shell thicker, maybe use more infill. Infill doesn't do much. Put that material in the shell. And only once you've exhausted the options of making your parts chunkier, thicker, putting more material into the part, and then you should start looking into using more high-end materials like the PPA, the PPS, HDPLA, I think is a really good option if that is a material that you can work with. Using a cheaper material and more of it is always going to be a more efficient and cheaper option versus thinking you need the highest end material. That was interesting for me. I hope it was interesting for you guys too. Thank you as always for watching. Keep on making, take care of yourselves, and I'll see you in the next one. Bye.